Good morning. I would like to thank you for attending today our session, despite the difficulties regarding the weather and the strikes. I think that this session is really interesting because it highlights the multidimensional nature in research and psychological research in general. I'm D Vlastos, and I am an MSc Health Psychology student, and I'm here to talk to you about my project, which is an eye tracking study entitled Interfering with Selective Attention, Effects of Backward Masking on Saccadic Reaction Time and Pupil Size. Up to now, we do know that brain regions related to higher-level processing can be influenced by lower-level operations. Both top-down goal-driven and predictive signals contribute to bottom-up stimulus-driven information processing. The perception of facial expressions may involve both unconscious early visual processing as well as higher-level operations in order to make individuals aware of a stimulus and of its influence. Affective processes seem to demonstrate and form perception on sensory pathways, while in terms of vision, possible influences on oculomotor processes may force eyes to emotionally endogenous and exogenous cues. Existing studies on selective attention have focused independently on these cues, despite the fact that attention and awareness are driven by multiple attention gain control systems that may act simultaneously on visual pathways and also control the acquisition of neural responses. Individuals tend to process emotion-relevant information earlier than neutral, whereas threat-relevant cues attract attention rapidly in order to prioritize further and accurate processing for the manifestation of a potential response, even when cognitive resources are sufficient. From studies that used eye tracking as a method of measurement, we know that there are variable results when we investigate to what extent emotionally meaningful information impacts on the number of fixations, how long such stimuli must stay on screen before they elicit a response, what types of stimuli attract the very first saccades, and whether individual differences exist in these processes. Visual perception can be influenced by affective information, both behaviorally and neurally, while emotion-relevant information, cues, are processed more efficiently than neutral, supporting a negativity bias account in general, which demonstrates modulation of even early sensory processes by unpleasant negative visual stimuli. There is evidence to support that emotionally significant information has a greater effect on the number of fixations, attracts more the first saccades than neutral information, whereas individuals detect fearful faces faster than other types of stimuli. Maxtorley and Van Riekum in 2013, in an eye tracking study, they used emotional distractor images in a selective attention task, and they found saccadic changes each time a distractor was represented extrafoveally within the task, compared to neutral images, and concluded that the process of selection can be biased by motivation. However, there are literature contradictions in this topic. For instance, Pessoa in 2002, in an fMRI study, supported that the presentation of unattended emotional stimuli, such as fearful faces, does not elicit a response in the amygdala. Bicep, on the other hand, hypothesized that the amygdala responses to fearful faces vary depending on the participants' anxiety levels. For instance, highly anxious participants' responses were unaffected by attention, whereas low anxiety participants were more likely to respond to attended than unattended fearful faces. Oman, in 2007, in a study where galvanic skin responses were recorded, showed that unattended masked fearful faces cause a physiological response during a selective attention task, a finding which later confirmed through PET. Stepanovsky in 2007 finally hypothesized that the difference in findings may be due to participants being able to detect masked fearful faces as early as 17 milliseconds. So whether unattended masked fearful faces can activate emotionally relevant areas such as the amygdala and areas related to cognition such as the frontoparietal networks of attention has been debated for some time. One seemingly important factor is exposure time, with studies reporting that some participants could detect fearful faces as 17 milliseconds. However, existing studies on selective attention have focused independently either on exogenous or endogenous cues due to the difficulties involved in the quantification and measurement of affective processing. However, different sources of modulatory control act at the same time on visual pathways and also control the acquisition of neural responses. Additionally, little is known about the impact of potentially accessible but unattended fearful stimuli on the process of selective attention in particular, for example, interference with selection and recognition. So in order to conduct our study, we followed the guidelines by Holmquist in 2011, and we used to determine these guidelines the required number of participants to increase the precision of the data given the sampling rate of our tracking equipment. Thus, 47 student volunteers participated in our study. They had normal or corrected to normal vision, were in good health with no past history of psychiatric or neurological disorders, and gave their informed consent prior to inclusion. The experiment was approved by the Cardiff Metropolitan University Research and Ethics Committee and was in accordance with the Code of Ethics of the World Medical Association. Informed consent, of course, was obtained from all individuals participants included in the study. Interference in our experiment was introduced through the extrafoveal backward masking technique, and we had fearful to neutral or neutral to neutral faces that appeared on screen with a temporal variability of 17 milliseconds, 33 milliseconds, and 0 with no exposure to the distractors. The experiment was developed in Java in order to work with the eye tracker's software development kit, and an eye tracker was used to record saccadic behavior with a sampling rate of 60 Hz. We used 10 fearful and 9 neutral images, you can see there a sample, from the Vlastos set of emotional facial expression pictures as task-irrelevant stimuli, as well as 8 control target images that were depicting geometric shapes with no possible emotional content. Our study included a total of 360 trials split into 6 blocks of 60 trials. Each trial began with a fixation cross for 900 milliseconds, followed by a random neutral picture of a colored neutral geometric shape in foveal vision. That was the target. After another delay of 900 milliseconds, either a fearful or a neutral phase, the distractor, briefly appeared for a variable time window with either no interference, 1 frame, it was 17 milliseconds, and 33 milliseconds, above or below the fixation in a random manner. Next, a neutral face mask would replace the distractor. Half the trials would have fearful to neutral distractor, and the other half had a neutral to neutral distractor. And finally, the target and the non-target appeared left and right on the fixation cross, separated from their outer edge by a specific visual angle, and the participant could fixate on either the target, that was a successful trial, or the non-target, counted as a selection error, in order to move on to the next trial. We measured 3 continuous dependent variables, the total saccadic time from fixation to the peripheral target and the non-target, and that was the reaction time, the selection errors, and pupil size. And we had 2 independent categorical variables, the exposure to the distractor prior to masking, and the type of facial stimuli presentation, fearful to neutral or neutral to neutral faces. We used omnibus tests to look for the main effects and interactions between the variables, and post hoc tests to identify which groups showed significant differences. Our analysis showed that, regarding the reaction time, participants had an increased delayed reaction in selecting the correct match in trials that had a masked fearful distractor compared to trials with a masked neutral distractor, a finding which is in support of the general consensus that masked fearful faces can modulate the process of cognition. However, surprisingly, our results indicate that the effect of masked fearful faces on reaction time was stronger on shorter times at 17 milliseconds than 33 milliseconds. Regarding the pupil dilation, our study provides further evidence to support that masked fearful faces can affect pupil dilation, an effect that can be reliably measured using eye tracking. In trials with a masked fearful face distractor, pupil constriction was reduced when compared to trials with a masked neutral face distractor. Much like with reaction time, our results indicate that the constriction response was smaller in trials where the masked fearful face appeared for 17 milliseconds than in trials where the masked fearful face appeared for 33. Finally, we found that there was a significantly higher chance of selection errors in trials with masked fearful faces than trials with masked neutral faces, a finding that we anticipated. However, the exposure time to the masked distractor, regardless of valence, also had a significant impact on selection errors. It was in the opposite direction than expected. When not accounting for valence, short exposure times led to more errors than longer exposure times. Overall, our results suggest that exposure to masked fearful faces in extrafoveal vision for as low as 17 milliseconds is enough to produce a measurable physiological response and delay in the process of selection. The cause for the unexpected results mentioned before, highlighting the contradictions in the literature, is something that we aim to investigate in the future. However, we suspect that this may have more to do with the process of masking itself as a technique, perhaps due to the movement artifact sometimes caused when the mask is applied. So, okay, we're conducting a research, but we do care about the practical applications. Selective attention is fundamental to almost all learning tasks, which allows learners to focus on cognitive resources, on vital information, while ignoring unnecessary input, and by so doing facilitate internal cognitive processes. Faces provide an exceptional opportunity to study the generic mechanism of unconscious processing. Invisible faces constitutes also a convenient platform for researchers to address new questions and represent a promising tool in both academic and clinical domains. For instance, we can develop interventions to promote health, with several studies reporting that invisible emotional faces can be used for diagnosis and for measuring the effectiveness of intervention with patients suffering from depression. A question that arises is, would this or similar methods be effective for other psychiatric disorders as well, such as post-traumatic stress disorder? In the clinical domain, will autistic patients who do not fixate on eyes or fixate less compared to healthy participants, invisible faces also not fixate on eyes in invisible faces? It is possible also, using invisible faces, that we can reveal social phenomena that cannot be revealed using visible faces. For instance, racist biases that can be revealed reliably, possibly, by using invisible faces. And how can invisible faces be used in the future as lie detectors? And lastly, to develop computational models and machine interfaces to enhance the cognitive brain. For instance, in ADHD patients or patients with learning difficulties in general. Thank you. Any questions? Okay, we can move on to the next speaker.